Okay, this is about the internal physics practical, or the internal investigation. You will gain 4 credits towards your NCA for completing this. In fact, the standard number has been updated to 91521, the old number being 90774. So for this, you will be required to do all the following bullet points. Write a detailed method, measure quantities accurately, plot graphs to determine relationships, process that data that's in the table, process errors correctly, plot linear graphs with error bars, and write a conclusion with a mathematical relationship that includes the error from the graph. Write a discussion that details how valid the experiment is. So for writing a detailed method, what it means is that you need to include very clear descriptions of the procedure you used to ensure the experiment gave as accurate results as possible, and to make sure that has happened, you had to write about any error reduction techniques that you've used, or techniques to improve accuracy. For example, timing multiple oscillations to minimize human reaction error. Also timing oscillations at the midpoint above a reference mark to reduce random error due to parallax effects. And there are many others that you will come across. But basically your method needs to be a step-by-step procedure that includes these techniques of accuracy improvement. So here's an example. Number 1, step 1 if you like. Set up the apparatus according to this diagram, and you would include a diagram here that's clear and labelled and shows exactly how the apparatus was set up. Step 2, set the length to a constant value, L equals 0.5 meters. Check that it is constant before each trial. There's a little step that would impress the marker and shows that you are being careful about procedure and accuracy improvement. Step 3, to reduce human reaction error, time multiple oscillations so that each trial measurement is at least 10 seconds. This is very important, as we discussed in class. It does reduce the percentage error that occurs with each trial, and so on. So you'd have more steps, obviously, to round out the method. This would be the first few steps to a simple pendulum investigation, which we have to practice with in class. Okay, so how to process errors correctly. Just to remind you, you need to have at least 3 trials for each length measured, if you're doing the simple pendulum one, for example. And then use those 3 trial measurements to find an average and the half-range error as well as the final period. So here's a table of data. It's slightly muddled up. This figure here should be 28.30, and the error I've calculated to be 0.05, and therefore 2.83 and 0.01 plus or minus. So how to get to those figures? We'll just run through it quickly. In this case, we've measured some lengths, 2 meters and 20 centimeters, or 0.2 meters. We have 3 trial sets of data, so 10 times the oscillation. So we're using n equals 10 in each case, even though for the 20 centimeter data it does slip underneath 10 seconds. It's only just underneath 10 seconds. The percentage error would still be pretty small. So looking at the first row then, these 3 figures here, the average value is clearly the last one. It sits right in between the other 2, so that's nice and easy. To find the error, the half-range error, you need to take away the smallest value, which in this case happens to be the 28.25. Take that away from the largest value, 28.35. Divide by 2, and you should get 0.5. And then divide by 10. Sorry, you should get 0.05 as a difference. And that's where the error comes from. And then to get this last figure here, the 0.01, we need to divide the 0.05 figure by 10. Now that would actually give us, in fact, 0.005, and that needs to be rounded up to at least 100th of a second, because that is the smallest error for a stopwatch. And looking at the last row then, just to see where these numbers come from, the average of these three values here is 8.71, and the half-range error, it would be found from 9.21, subtract 8.01, and then divide by 2, and you should get plus or minus 0.6. Then dividing by 10 to give us the final error in the period, which of course is the 8.71 divided by 10, getting 0.87 in this case. Notice we don't have any more figures after the 7 because of this error in that decimal place. Okay, this is just a reminder of how to process errors with functions. For example, when the period is squared, each error needs to be processed as follows. You need to calculate the percentage error for the period t, multiply that percentage error by 2, and this is because of the squared function. So t to the power of 2, you use that number, whatever that power is, and you multiply it into the percentage error that you've calculated for t. Now you can use that percentage error to find the actual error of the t squared, that should say, value, and round that to 1 dp. Very importantly, you must always round your actual errors to 1 dp. And you can see the example below. Just if you follow the logic, this bit of working here goes with this line, and this bit of working here goes into there, and this is the final answer. But take yourself through it slowly so you can follow the mathematics there. Now, for plotting graphs, you need to be able to identify what relationship is indicated by a non-linear graph. So there are several different curves you need to become familiar with. Once you know the type of relationship, you need to process the independent variable, for example, the length of a pendulum, in order to plot a linear graph. You then find the gradient, the y-intercept, and the associated errors of that linear graph. You use that information to write the concluding mathematical relationship in the format of y equals mx plus c, which describes a straight line. Now, for example, for a simple pendulum investigation of how length L affects the period capital T, it is found that the equation is T equals m with the gradient times the square root of L plus c, where in fact c is basically 0. And of course this gradient also needs to have an associated error written in there. So in fact your final equation will look something like this. You'd have some value here, we'll just call it delta m, the error in the gradient m, times the square root of L. And there'd be no intercept essentially, because for a simple pendulum that is in fact 0. Now, where does that little error delta m come from? Well, just reminding you, it comes from the difference in the best fit line gradient and the error line gradient. Finally, to gain something better than achieved, you need to write a good discussion at the end of the report, and it should be written in a way that summarizes how valid your conclusions are based on your data, how accurate and precise your method was that allowed you to reach this conclusion. You should also relate your findings to the real-world situation on which the assessment task was based. And you should also point out any limitations to those findings. So you might have modelled the real-world situation with a simpler apparatus, and you need to acknowledge that and say, and sort of infer what differences might occur in the real-world situation that your model, your investigative model, has not taken into account. For example, when comparing some pendulum data to a real playground swing made from chains and greased hinges, the period of oscillation may not be exactly the same for equal length of pendulum and swing, because, and you'd have to write some justification as to why that might be the case. You might also talk about the accuracy of, how you made sure things were accurate. So you might have a statement like this: when timing 20 oscillations, I made sure to stand opposite the clamp stand to use it as a solid reference point. This helped minimize parallax error. So this shows, that you sort of arguing that your data and your gathering of data was indeed accurate. It's also important to be able to refer to the mathematics in some way. For example, there could be a constant, a value for the acceleration due to gravity, as an example, for a simple pendulum that sort of pops out from the mathematics. And you should be able to compare the known value of G in this case to what you have actually calculated in your report, and therefore use that idea as whether to sort of justify how accurate or how valid your investigation was.